Dear students, today we are going to discuss about P-type semiconductor. Here also we are going to discuss two derivation part. First one is the Fermi energy level and the second one is carrier concentration in P-type semiconductor. So in this video I am going to explain about where the Fermi energy level lies and what is the expression for that, and then how the Fermi energy level changes according with temperature and the impurity concentration. Okay, let us go to the derivation part now. Okay, so how the p-type semiconductor starts, that means how it forms. Okay, so the p-type semiconductor can be formed with the help of trivalent impurities. So trivalent impurities are added with semiconductor, it forms p-type semiconductor. So now trivalent impurities, that means those elements are having the valence electrons 3. So example for trivalent impurities is boron, aluminum, gallium, indium, etc. These are the trivalent impurities. These impurities are added with germanium or silicon, that is our semiconductor. Germanium or silicon, it produces the p-type semiconductor. So this already we know that. Okay, so how this energy level diagram changes when trivalent impurity is added. So normally we will have the valency band at the lower energy and the conduction band will be at the upper energy. And then if we add this trivalent impurities, so trivalent impurities is also known as acceptor impurities. Why? Because it has only 3 valency electrons in the outermost orbit, so that these atoms are ready to accept the electrons. Okay, ready to accept the electrons. So electrons will come from valency band, so it is ready to accept. So this acceptor energy level just above the valency band. The acceptor energy level lies just above the valency band. So here the valency band energy is represented by EV and the acceptor energy level is represented by EA. Okay, so what is EA here? EA is the acceptor energy level. Okay, so in this case of p-type semiconductor, the valency band and the Fermi energy lies in between the acceptor energy level and the valency band. Okay, so EF is equal to EA plus EV divided by 2. Okay, so this expression only we are going to prove in this derivation part. So the EF lies exactly in between the acceptor energy level and the valency band. Okay, so this is what. Now generally the electrons will present in the valency band. Okay, so if at a room temperature or at low temperature, the electrons absorbs the energy and then it will jump to the acceptor energy level. So the electrons will go to the acceptor energy level. Okay, for example, here I mentioned 3 electrons. If this 3 electrons goes to acceptor energy level, means it creates holes in the valency band. So what we are going to discuss, that number of holes in the valency band is equal to number of electrons in the acceptor energy level. That is NH, number of holes in the valency band, is equal to number of electrons in the acceptor energy level. So our duty is to find how many number of holes present in the valency band as well as number of electrons in the acceptor energy level. Okay, so now let us start the discussion. The first step, what I am going to write is number of holes in the valency band. So number of holes in the valency band. As we know well, so that is P we mentioned, but here I am going to write it as N suffix H, which is equal to 2 into 2 pi m H star KT divided by H square whole to the power of 3 by 2. Okay, exponential of EV minus EF divided by KT. So this is the expression that represents number of holes in the valency band. So this I am considering equation number 1. Right. The next step is we have to find out number of electrons in the acceptor energy level. Number of electrons in the acceptor energy level. Acceptor energy level. So how to find? Number of electrons is represented by N or N suffix E. Okay. So how can we find the number of electrons? By means of Z of E into dE into, we are talking about electrons. So electron occupancy can be represented by F of E. Right. So here we are talking about acceptor energy level. So this E is replaced by EA. E is replaced by EA. So Z of EA into dA, I am going to write it as NA. Okay, NA into F of EA. What is this NA? Okay, let me explain this. Z of EA into dEA is nothing but density of energy states. Density of energy states. That means how many number of energy states available to occupy the electrons. Okay, so density of energy states, which is nothing but NA. Okay, density of acceptor energy states. Acceptor energy state. So that I am going to replace this Z of EA into dEA by NA. Right. So this part over. So this I am considering equation number 2. Okay. Next step is we have to consider F of EA. So what is F of EA? F of EA is the Fermi energy distribution. So as we know well, the formula of F of E is 1 by 1 plus exponential of E minus EF divided by KT. E minus EF divided by KT. Here E should be replaced by EA. EA minus EF divided by KT. Okay. So this discussion already we have done in number of electrons in the conduction band derivation part. So what is the discussion? The same thing I am going to follow here also. Now you see in this diagram, okay, EA is here. Okay, actually this is EV valency band. EA is here. After that only EF will be. Okay, in between these two only EF will be there. So EA minus EF, it is the positive quantity. EA minus EF is the positive quantity. So EA minus EF is very much greater than 1. So that exponential of EA minus EF divided by KT is also very much greater than 1. That is the reason I am going to neglect 1 from denominator. Okay, so that F of EA is equal to 1 divided by, I neglected this 1 from the denominator, only exponential of EA minus EF divided by KT is existing. So this is equation number 3. Now next step, what we are doing is substitute equation 3 in equation 2. So what is equation 2? In equation 2 we discussed about number of electrons in the acceptor energy level. So Na, in place of F of EA I am going to write 1 divided by exponential of EA minus EF divided by KT. Okay, so this is equation number 4. So now in equation 1 we have number of number of holes in the valency band, and this is okay, equation 1, number of holes in the valency band, and then in next equation 4 gives number of electrons in the acceptor energy level. So now we have to find out the Fermi energy formula. So how can we find? Now I am going to find Fermi energy in p-type semiconductor. Okay, Fermi energy is represented by EF. Okay, so two conditions as we know well. One is number of electrons is equal to number of holes, and then at T is equal to 0 Kelvin. These two conditions we have to follow to find the Fermi energy. So now number of holes in the valency band is equal to number of electrons in the acceptor energy level. So this gives equation 1, and then this can be given by equation 4. So accordingly, I will substitute the values here. 2 into 2 pi m h star k t divided by h square whole to the power of 3 by 2. Okay, exponential of EV minus EF divided by KT, which is equal to equation 4, that is NA, okay, into 1 divided by exponential of EA minus EF divided by KT. So afterwards the same steps we have to follow to find the value of EF. So here the exponential term is in denominator. When it comes to this side, it will go to the numerator. Remaining all the terms will go that side. So how can I write? Exponential of EV minus EF divided by KT, okay, into this term will come here. So exponential of EA minus EF divided by KT, okay, which is equal to NA divided by all the terms 2 into 2 pi m h star KT divided by h square whole to the power of 3 by 2. Right? So next, exponential A into exponential B. How can we write exponential of A plus B? So A is EV minus EF plus, okay, what is this? EA minus EF divided by KT, which is equal to NA divided by 2 pi m h star KT divided by h square whole to the power of 3 by 2. So what is this? Minus EF minus EF. So how can we write? Exponential of minus 2EF, okay, plus EV plus EA divided by KT, which is equal to NA divided by 2 pi m h star KT divided by h square whole to the power of 3 by 2. Right? So next step here, exponential A and B, exponential A plus B. I am going to take the logarithm. Okay, so to remove the exponential term, taking log on both sides. So what will happen? Log and exponential will be cancelled. Minus 2EF plus EV plus EA, okay, KT will be here, okay, is equal to log of NA divided by 2 pi m h star KT divided by h square whole to the power of 3 by 2. Right? Another thing also we can do. This KT I am going to multiply over there. So minus 2EF plus EV plus EA is equal to KT. This KT I am multiplying here. Log of NA divided by 2 pi m h star KT divided by h square whole to the power of 3 by 2. Okay. Next step, you see minus 2EF is here. I need plus 2EF. So this term I am going to take to the after the equal sign, and then this term will come here. So how can I write? Listen carefully. EV plus EA. EV plus EA is there, plus, okay, sorry, minus sign will come. Yeah, minus sign will come. This term is here plus. So when it comes opposite side, minus KT log of NA divided by 2 pi m h star KT divided by h square whole to the power of 3 by 2, which is equal to 2EF. I need only EF, so the 2 will come this side. Two terms are there, both sides, both term it will divide. So I am going to write like this. EF I am taking this side, which is equal to, what is the first term? EV plus EA divided by 2, right? Minus KT by 2 log of NA divided by 2 into 2 pi mH star KT divided by H square whole to the power of 3 by 2. Right? Okay, this equation you consider it as 5. To find the carrier concentration, we need this value, EF value. So make a note on this. Okay, this information is very important to find the carrier concentration in p-type semiconductor. The next step is ours, that is at T is equal to 0 Kelvin. So what will happen? The second term totally becomes 0. So that we will get EF is equal to EV plus EA divided by 2. Okay, what is the meaning of that? The Fermi energy lies between valency band and the acceptor energy level. So diagrammatically already we have seen this, but now we proved expression also. EF is equal to EV plus EA by 2. Okay, I write here Fermi energy lies exactly in between the valency band and the acceptor energy level. Okay, that's what we proved. So EF is equal to EV plus EA by 2. Okay, now I completed the Fermi energy formula. So next what we have to discuss, what is the variation of Fermi energy with temperature. Okay, so now I will start. Fermi energy varies with temperature and impurity concentration. Okay, so two things, one is temperature, okay, and another one is impurity concentration, right? So let us see one by one. So for this we need the energy level diagram again. So the lower energy band is called valency band, the upper energy band is called conduction band. Okay, so this is valency band, okay, and then this is conduction band. According to energy the variation happens. So this is energy. Okay, so now you see acceptor energy level just above the valency band. So this is EA and this is EV. Just now we proved that Fermi energy lies in between this acceptor energy level and the valency band. So EF is equal to EA plus EV divided by 2 for p-type semiconductor. Right? This is what now we proved. But what they are asking, if you increase the temperature, this will happen at a temperature T is equal to 0 Kelvin. If you increase the temperature, how the Fermi energy varies. Okay. Now you see, in case of intrinsic semiconductor, the Fermi energy level lies in between the valency band and the conduction band. So EV plus EC divided by 2 for intrinsic semiconductor. Right? So now for a p-type semiconductor, if you increase the temperature, that time slowly it will try to reach the intrinsic semiconductor. try to reach the intrinsic semiconductor. Okay, so that this is for acceptor energy is equal to 10 power 21 atoms per meter cube. Okay, same thing if you add more concentration of impurity, so that it will be like this. Okay, that is Na is equal to 10 power 24 atoms per meter cube. Okay, so three variations we have discussed. What are the three variations? Generally, the Fermi energy level lies in between EA and EV, that is in between acceptor energy level and valency band at a temperature T is equal to 0 Kelvin. If suppose if you are increasing the temperature, so that the Fermi energy of the P type tries to go to reach the Fermi energy of intrinsic semiconductor, right? Okay, if the concentration is 10 power 21, if you increase the concentration, then it will not reach up to intrinsic, it will be in between this. Okay, so this is what the Fermi energy variation with temperature and impurity concentration. I hope you understand this variation as well as the expression for Fermi energy for p-type semiconductor. So please go through this derivation part. If you find any difficulty anyway, you can ask in the comment box. Okay, so thank you everyone.